Hello everybody, how's it going? Last night I had the pleasure of presenting in the Deep Learners reading group as a part of the Fast AI community. So I recorded this presentation and I wanted to put that up here on YouTube for anybody to listen to and to learn from. And I also wanted to just introduce myself a little bit. So my name is Jack Toll and I run a blog at jacktoll.net. So that's my personal website. I live in Sydney, Australia, and I'm 21 years old. And I'm currently attending the University of Technology, Sydney, taking my Bachelor's of Artificial Intelligence. And I started this in 2023 and I'm still going now. So last night I presented this notebook which is pretty much an introduction to LangChain. So I introduced the framework of what LangChain is, where it sort of fits in the whole NLP, LLM production sphere. And I also wanted to do a bit of a demonstration about some of the various components that sort of make up LangChain and how these different components work together. And I also wanted to finish off this presentation with a end-to-end RAG walkthrough, going through a real example, reading from a textbook PDF that I have, uploading it to a Pinecone vector database, and then doing a retrieval from that database based on a user's query, and then putting that through to a prompt template, which ultimately gets sent to an inference model. So in this notebook presentation, I covered all of that. The audience that is intended for this presentation is kind of anybody, in this sort of sphere. So AI enthusiasts, machine learning, deep learning, developers, researchers, just, anybody that's interested really. So yeah, if you want to get in contact with me, my email is contact@jacktoll.net, or I have some of my other social and creative networks linked on my website, jacktoll.net. So without further ado, here's the presentation. I hope you enjoy and I hope you learn something, and I'll see you guys later. So yeah, LangChain is a software framework that pretty much is created by the LangChain company. They have various different products that sort of aid in the development, testing, evaluation, management, and deployment of LLM-powered AI applications. So let's just get started with the introduction. So on langchain.com, we find, so that's just the landing page for the main LangChain company. So it's a software company first and foremost. And and as I mentioned earlier, create various products for the development of AI-powered, LLM-powered AI applications. So the naming scheme can get a little bit confusing because LangChain is the name of the company, but it's also the name of the main product that they have going on as well. So one of the main products is LangChain, and LangChain is a framework that contains multiple packages, and it aims to be a flexible yet also an abstract AI toolkit that provides all of these modular components which work together to create LLM-powered software applications. And so the LangChain product is going to be the focus of today's application, because I just think it's the most consequential and sort of like the most important of the different things that they offer. So the LangChain product contains four separate packages, four main packages. We have the LangChain core, LangChain community, we have some partner packages, and LangChain itself. The LangChain core is just base abstraction. So it's just the basic different broad components that sort of make up the framework. These aren't third-party integrations. They are made by LangChain themselves. And it's meant to be lightweight by design. LangChain community is community-maintained third-party integrations for various components. So if you think about it, LangChain doesn't need to actually sort of invent and create all of the different components themselves. It would be really smart if there was a way that we could sort of leverage all the years of hard work from a bunch of developers and researchers that have sort of created all of these amazing little helping packages, like little PDF parsers and stuff like that, that we can sort of use and integrate into our LLM applications. We also have partner packages, so it's a bit of an extension of the LangChain community packages, other partner packages. So for some bigger companies like OpenAI, Anthropic, Pinecone, and also like Quadrant, there's like quite a few of them. We have sort of these partner packages. So these are the libraries for those have been separated from the LangChain community packages, just to provide better support for them and just to make sure that they're in their own sort of little area. And then lastly, we have the main LangChain package, which contains all of the proprietary LangChainy stuff that was kind of created by the LangChain company, right? So this is going to be chains, agents, different retrieval strategies, all of the stuff that's really core to like an application architecture. And these components are not specific to any one integration, but they're actually more generic across all integrations. So I have this little example here, just showing some of the various sort of broad components that sort of are part of the LangChain product, right? So we have tools, models, text splitters, output passes of the model, document loaders, vector stores, just a bunch of different helping building blocks that sort of work together. Now, it's worth noting that LangChain has two additional products. They have LangSmith and LangServe. So LangSmith is really cool. So it's an interpretability platform. So when I think interpretability in this context, I think of stuff like RAG, chain of thought, agentic functions. Anytime where in our LLM application, we have some mechanism that's sort of retrieving some data, or it's we're going through some like chain of thought, or we're calling some functions and we're getting some data from like a third-party interface, and we want to see what data that is, maybe like weather information or something. Having a way to actually look at like what's being retrieved from, like what's the model retrieving, what's being sent through, all that sort of stuff. That's what we can see in the LangSmith dashboard. So this is mainly for debugging, testing, evaluating, monitoring the responses from the LLM. And then they also have LangServe, which is also really cool. So LangServe essentially is a package which is built on top of Fast API, and it makes it just a bit easier to deploy your LangChains as APIs. So if you think about it, if you have a LLM-powered application that's doing some complex sort of chain of thought stuff and some RAG stuff sort of happening in the background, since we just have all of these different components that are sort of being chained together in this, all the links of the chain are there, it would be really cool, since that's quite abstract, if we can make that into an API. So we can so anybody can sort of plug in their front-end user interface to your sort of backend. So that's sort of what LangServe provides. So chains to REST APIs for production-ready applications. So when I'm thinking of LangChain, I'm essentially thinking of two main points, two things that it does really well, and sort of the main purpose of it. It's a software framework designed to simplify the integration of LLMs into application by providing these modular components. So that's the first part. And then the second part is debugging, testing, evaluating, and deploying LLM applications more efficiently using these various products and modular components. So we went through what some of the components were before, but I'll just quickly list them out again. So these components include stuff like a bunch of different language models. We have a bunch of different companies and a bunch of different open source models, right? And we want one centralized hub to be able to kind of use them effectively in our applications. So these components include LLMs, embedding models, vector stores, document loaders, and tools, which is just like agentic functionality and much more. So in this presentation, we're going to be exploring just some implementations of some of these components, and then we're going to conclude with a demonstration of a small-scale notebook-based RAG prototype, which is going to show how these elements and components can be integrated together and sort of function cohesively. And I think you'll be surprised how sort of simple it is and how easy they make it for us. So covering a few LangChain components, and then we're going to do a brief overview of RAG. So there are far too many components to cover all of them here. So I'm just going to be covering sort of the ones that I think are the most important and very intuitive to understand. So here we go. The first ones are document loaders. So we're going to be covering a PDF document loader and a CSV document loader. So I have this directory here, example data, and I have this research paper, Efficient World Models with Context-Aware Tokenization, that I just got from a Discord server, and also a CSV file containing archive metadata. This has just been passed, this hasn't been processed, so this is just downloaded for, I think, just a few days ago. So the first thing that we'll notice with the import here, we're going to be importing from the main LangChain module, from document loaders, which is the submodule, we're going to be loading in PyPDF loader. And then we just create an instance of the object and we set it to PDF loader example. And then we pass through our PDF. we set pages equal to our to the loader, and then we use the load method, and then we will print out pages and see what it looks like. So here I'm just printing out the first 5, and as you can see, it's just going to be a list, and inside each item in the list is going to be all the content of each page. And then at the very end, we're also going to have a dictionary of metadata, which tells us where the data originally came from and the page that it originally came from as well. So that's how easy it is to load a PDF into LangChain. It's extremely similar for the CSV document loader. So we're going to be importing the CSV loader, and we're going to be doing the exact same things. And here you can see that each row here, or each item in the list, is just going to be in the page content attribute. We have the document ID in this case, the authors, and all the other fields. And then at the very end, we have that metadata dictionary again that just has the source and the row that it came from as well. Now, they also have chat model integrations, as mentioned earlier. So I'm just going to be importing Chat Anthropic from LangChain Anthropic. So this is an example of one of their sort of official integrations with sort of a bigger company model. So that's a dedicated module because that's being updated very often. And then it's really easy to actually create an instance of a Claude LLM. So we literally just have to create a Chat Anthropic object where we pass through a model, temperature, max tokens. You can even set that to none, and then timeout. If we use the invoke method on a Claude model, and we set, and then we pass through a query, like what is the meaning of life, we can really easily here, it'll send that query through to the model, and then it'll just print out the response from it. So in literally like 3 lines of code here, where what we can already in a coding environment start interacting with the Claude API and start getting responses, which is really it's really easy compared to the API, the Anthropic API that they give us. Lastly, in this section, we have vector stores. So here I'm just going to be importing Pinecone vector store and OpenAI embeddings from the Pinecone and OpenAI integration. I'm just going to be setting the embedding model to, again, an OpenAI embedding model object, passing through the model that I want, and also going to be creating my vector store, passing through an example, archive example index that I created. So here is probably an important time to bring this across. So here I have, in my Pinecone dashboard, I've created a new collection for the LangChain presentation. I've populated this archive example index with 400 vectors, which is like data of different research papers from that were uploaded a few days ago. So if we look at what the data actually looks like, we see that each text in the vector database is the title connected with the authors, and then it also has a corresponding document ID, sort of saying the document ID for that paper. So if I run this, we're going to run the embedding model and load in the Pinecone vector store using the from existing index method. And then this is really cool. We can set a search results variable equal to, but we can run a similarity search on our vector store, and we can pass through a query and a K number. So K is just going to be the amount of things to retrieve from the vector store, and then our query is going to be like the title of a paper. So I can actually now just copy this one here, pass this through here, and then do this. And we can see that the first result that comes up is the paper that we want, and we can see the metadata here as well. And these are the top 5 most similar papers to this query. And this is sort of how the metadata search engine works for my archive RAG assistant application. So with that covered, so that's just a few components covered and sort of the implementations, and I think you guys get the idea. We're just going to have to, we just import the little subcomponent that we're after from the correct integration, from the correct package, and then we can start using them really easily, and the syntax is pretty intuitive and easy to understand. So now we're going to go through just a brief review of RAG. So for anybody that's not aware, but I think all of you are going to be aware, but RAG stands for Retrieval Augmented Generation. So there's a retrieval, an augmentation, and a generation component to it. The RAG pipeline, as we call it, consists of a few different parts which all work together to allow a language model to generate reliable and accurate information based on retrieved context. So, I mean, even as I described that there, it sounds like an amazing use case for LangChain, because we know that a RAG pipeline has all of these different moving parts, and so having sort of this library, this framework that provides all of these different components that all sort of work together seamlessly is a really good use case. So we pass through the user's query and the retrieved context dynamically to a prompt template. And the prompt template, we design it such that it leverages an LLM's ability to follow system-level instructions when directed, and also the fact that we can pass through content as variables to the model in like the Python programming language. So here I just have an example of the prompt template. So the instructions are, your job is to answer the user's query using only the provided context. Keep your answer grounded in the facts of the provided context. If the context does not contain the facts needed to answer the user's query, return, I do not have enough information available to accurately answer the question. And then we pass through our context and our user query dynamically into the template here. So how does the context actually get retrieved? So the idea is that we take our external documents to begin with, maybe a PDF, CSV file, TXT file, as I showed above, and we use some heuristic to split this text. So perhaps we specify a character number, so we split after n number of characters in the chunk, or if we're going to be splitting sort of code text, we can split on certain tags in there to sort of, because if we just use a character splitter, a recursive character splitter with code, maybe it'll cut off in the middle of a code and that'll just break up the context and it won't perform very well. So it's nice that we have sort of different mechanisms to split the text, and LangChain offers many different types of character splitter options as well, on HTML, on Markdown, all sorts of different text types. So if our splits are too small, say we split on sentences, we can combine a few sentences together to create a chunk of text. If we take these chunks of text and we pass them through a sentence embedding model, which is just a special embedding model that has been trained to be able to accurately embed sentences and chunks of text and sort of keep the contextual and semantic information of the chunk to be able to represent that. So if we pass this through to the embedding model, and then we can upload these embedding vectors to a vector database such as Pinecone. Now, when a user enters a query, if we encode that query using the same embedding model that we did when we originally, like the same embedding model that we used to embed the chunk, we can then perform a cosine similarity between all the vectors in the database with respect to the user's query vector. And then we just retrieve the top k most similar chunks of text. So the top, and you can specify the number. So I chose 5 earlier, but in RAG settings, you might choose 10 or 15 chunks depending on the type of data that you're working with. And then lastly, if we save the retrieved context to a context variable, and we also save the user query to a user query variable as they enter it, then I'm sure you can see that it's really easy to just dynamically pass through the context and the user query to the prompt template. And then we can pass the prompt template through to the inference model, and then the inference model will generate the response for us. So I just have a diagram sort of showing this. I'm not going to go through it all again because I just did now, but as you can see, we just start with external documents at the top, and that's one entry point, and the other entry point is going to be the user query, and then they all sort of connect up at the very end to where we get our output that is sort of based upon our original documents and the user query. So we're going to be going through a brief textbook RAG demonstration using LangChain, only LangChain components. So the example is going to be this. I have a textbook here, Machine Learning and Algorithmic Perspective, 2nd edition. So this is the PDF for a whole big textbook. And the idea, the ultimate goal is to be able to do that we want a RAG question answering assistant, basically, with respect to this one textbook. So the first thing that we're going to do is go over our imports. So just like before, we're going to be using the PyPDF loader because our PDF document is, the textbook is in a PDF format. We're going to be using the recursive character text splitter from the LangChain .textSplitter submodule. Here we have the LangChain Hugging Face and LangChain Pinecone integrations, where we're going to be using the Hugging Face embedding model, which is just sort of a wrapper around the sentence transformers model that I'm sure some of you have used. So this will be doing the embedding locally on my machine. And then we also have the Pinecone vector store, which allows us to interact with our vector store. So I have another index in my Pinecone collection here called textbook vector store. It's empty at the moment. I set the dimensions to 768 for it because that's the amount of dimensions that the Hugging Face embedding model encodes to. So if we define, so the first thing we do is define our PDF loader and our text splitter. And we pass through the path for the textbook, and then we set the chunk size to 500 characters, the chunk overlap to 50, and the length function to len, which is just going to be counting the characters. Now, what's really convenient is that with the PyPDF loader, there's a bunch of different methods. There's just there's a standard load method, but there's also a load and split, which is really cool because that means that we can sort of hit two birds with one stone. So we can use the PDF loader to load our document in, and then we can pass through as an argument our text splitter, and then we can save that to the chunks variable. So if we do that, it's currently reading and it's splitting this textbook into all of its different chunks. And that only takes about 9 seconds to do. Now, if we actually look at what these chunks look like, it's in the same sort of format as we had before. So we have this one documents list, and then the main content of each chunk is going to be stored in the page content attribute. And then really importantly, at the very end, we again have the metadata, which tells us the source. So this came from this textbook, which it did, and the page from which the chunk originally came from. And this is really important because whenever you're kind of creating a RAG application, you always want sort of this transparency. You always want to be able to tell the user exactly what data, like where the data came from that sort of formulated the response from the LLM, so they can always cross-check that later. And this is exactly where Langsmith would come in handy, because if we have our application, it would tell us the chunks that get retrieved, and then it would also tell us the sort of the metadata for that chunk. As a nice little sanity check, I often like to look at the lengths of the chunks list to have a look at the amount of chunks that we have. And given that this is a whole textbook and we chose a 500 character size for the chunks, 2,285 chunks makes sense. Next, we're going to be setting up our embedding model and our textbook vector store. So the embedding model is just going to be, we're going to set it to this Hugging Face embeddings object. And then our textbook vector store, just like before, we're going to be setting it up, but instead of doing it to the archive example index, we're doing it to the textbook vector store index, which is currently empty. And it's important that we pass through our embedding model here so it knows what embedding model to use when we start uploading and retrieving data from the to and from the vector store. So that should only take a second. Next, we want to separate out the page content and the metadata respectively. And we want each, so currently it's in this format, which we can't really just upload extremely easily. So we're going to be setting our text and metadata as variable, and it actually is quite simple. We just use a for loop for chunk and chunks, and then we just do a chunk.page content, and we just append it to the text variable, and we're doing a little list comprehension here, so we don't even have to specify that we want it as a list. It's just going to automatically do that. Same exact thing for metadatas, where we just look at the page and the source, and we just kind of loop through it. So we should have two variables that are the exact same length that sort of have the corresponding page content and the metadata for each chunk there. Now we can see what this looks like separated. So if we print out the first 5 texts and the first 5 metadatas, we see that we have this really nice list of metadata and this nice list of the corresponding metadata for each chunk there. And now it's actually really easy. So this is kind of the power of LangChain. We might actually, intuitively, it might seem a bit more difficult than this to sort of to upload all of our data, the corresponding data to the Pinecone database and to retrieve it and stuff like that. But here we just use the really simple from text method, passing through our text, our embedding model, our metadatas, and the index. And right now, it's going to be in the process of uploading our chunks and that metadata to the vector store here. Now, there's a really important caveat, something that I still don't understand, even though I've been doing a lot of debugging myself. For some reason, and I think it's a problem when we're making API calls to Pinecone, when we're actually sending the data there. Interestingly enough, even though we only have 2,285 items in the text and the metadatas, right? Like that's just the amount of chunks that we have. This number sometimes goes up by like an extra 100 or something like that. It doesn't happen all the time, and it's really hard to reproduce the error, but it's just a little thing that I've noticed. So we'll see if it happens this time. Actually inspecting the data that's getting uploaded, we can see here that we have chunks of 500 characters of this textbook. We have the corresponding page that that chunk came from and the document from which it originally came from as well. So that's really cool. Now, I often like to open up the original textbook. We can copy a bit of the chunk, do a little Control F. We'll find it. This says it came from page 26. And as you can see, page 26. So that's really cool. Now we have a way of sort of confirming where each chunk came from. Let's have a look at the amount that, yeah, see, it uploaded an extra 200, maybe duplicates. I have no idea where the data is coming from, but I think it's just some discrepancy in the, to do with the API. So I'll bring that over here. Here we go. So now that everything has been uploaded, and even though we just confirmed it by actually looking at the vector store, I created this little function, retrieve and display, which essentially we can pass through just a query. It's going to get the top 5 most similar, and then it's going to give us the print out the text component, the document component, the source that it came from, and also the page from which it came from as well. So if I pass through, tell me about neural networks. My bad. There it is. Hold on. It's going to do the similarity check. It's going to print out the top 5, and then we can see that all of these chunks do in fact contain some information about neural networks in there. And then again, we see the metadata. So now that we've kind of done that in this sort of exploratory manner, looking at all the different bits, I like to put it in a function. So this is just going to be the imports and the global variables that we need, and this is it. So this is all the code required to load in any PDF that we want, do whatever splitting, uploading, well, embedding, and then uploading, and then we get a little message telling us, you know, the metadata that's been uploaded. And then if we run that, it'll just re-upload everything again. So an exercise, if you want to try this on your own, it would be really cool to see if somebody can just really easily sub this out, the PyPDF loader with the PyPDF directory loader, and you can load a variety of different PDFs at once. And you can do this on your own notes, documents, textbooks, whatever. So now that we have all of the information uploaded to the vector store, it's time to actually do the retrieval and the actual like RAG component of this. So we're going to focus on the retrieval and the generation here. So like always, we're going to start with the imports. We've got OpenAI, LangChain core. So this is from LangChain core. We're going to be importing the chat prompt template, and then again, Hugging Face and Pinecone. Now the template is really cool. So this is how we're actually going to be creating that prompt template that we talked about earlier. So here we use the from messages method, and then we sort of create this list of different items that are essentially system messages, human messages, and AI messages. And this is in the format that a GPT model sort of expects. So it's all fully compatible. So here we have the system instruction, just like before. So using only the provided context to answer the user's query. And then, yeah, it'll tell us if it can't. And then we pass through the query and the context. Just like with the Anthropic model, we can really easily create a LLM just by using the chat OpenAI object passing through. We're going to be using a GPT-4o model, set the temperature, max tokens, and a timeout. We need a mechanism to capture a user query. So we're just going to be using Python's inbuilt input function, and we're going to be saving that to a user query variable. So in this case, I'll just say, tell me about neural networks, just like before. Even though it's a bit redundant, I'll be once again redefining the embedding model and textbook vector store. And also, just like before, we're going to be saving our retrieve context to a similarity search with respect to the user query that we just entered, and we're setting the K value to 10. And then we can print out what the retrieve context looks like. So that was quite quick. Now we just need a method to actually extract the page content itself. So we just use that really simple for loop, and we save that to the context variable. So now we have one list containing all of the context that was retrieved based on that user query. Now, this is one of the coolest functions, I think, methods. We can do an invocation of our template, and we can set this to a variable prompt value. And then this is when we pass through as a dictionary our query and our context to user query and context. So this is how we're dynamically passing through our user query and context to the model. If I run that, and now we can again just use that invoke on the LLM, and we pass through as an argument here the prompt value, and then we can print out the response. And here we go. But now it's wrapped in this AI message, so we're just going to extract out the actual content, and we get neural networks are computational models inspired by the human brain. They consist of interconnected nodes or neurons that work together. So this is all information and data which came directly from the textbook. So we can be sure that the information is authoritative and correct and reliable and all that sort of stuff. Now, obviously, when we're talking about big pre-trained models like GPT-4o, we don't actually really worry about the reliability of, like what is a neural network, because those sorts of questions for a general pre-trained model like that are always going to sort of be correct just with the vast amount of training data. But I'm sure you can see the value in this system, because now we can start connecting up a language model to data which the model hasn't been trained on without having to fine tune it. So for a bit of fun, we can have a look at what's actually contained inside prompt value, so what's actually being sent, but this is a bit difficult to sort of understand. So we're just going to pass out the various components that we want, and we can see exactly as expected. The system instructions is exactly that. The context is this long list of context which has been sent to the model, the query, and then this is the response from the LLM. There. Time to put that into a function. So exactly the same steps, just kind of condensed down. And yeah, so that's that sort of RAG demonstration. There is one other bit that I wanted to cover before wrapping up. And I just found this out yesterday, but I wanted to cover this because just in the last week, we went through graph neural networks and graph RAG, and recently LangChain just released integrations with graphs, especially a Neo4j graph. So I created I'll quickly pull it up. I created a graph database using Neo4j, and I just loaded in a sample data set, which is just a classic movies data set. And we have a mechanism of doing graph retrieval as well. So walking through I don't have all the pros to go along with it, but I can just explain some of the code. But we're going to be utilizing two instances, two OpenAI instances, one for actually doing the retrieval, and then the other one for sort of passing it and making it into a bit more of a structured manner. And just like this, we can see when we ask a query, such as what movies has Tom Cruise played in, it's going to be it's in the exact same syntax as the other notebook. That's what's really great about LangChain, is that it follows the same sort of consistent pattern. So it's really easy to pick up like a new module that they have, and then we just format it, and then we can see that this data here, that it's retrieved from a graph database. And I want to pull up the data for it, because I thought this was quite interesting. Here we go. So we can see this is just a sample movies data set which shows essentially different movies and the directors. And so when we do this, when we send in a query such as what movies has Tom Cruise played in, it's going to be trying to figure out where's sort of the most likely candidates for where that answer is contained. And then it just retrieves those nodes, and then it returns it back to us. And then I just get the retrieved data and the query, and I prompt a new model saying, given the query, format the following data into a detailed and conversational sentence using the retrieved data. And then that's how we get the response. Tom Cruise has appeared in several movies, including A Few Good Men, Top Gun, Jerry Maguire. And then again, we just put this in a function, and then we can use that as many times as we want. So that sort of is the presentation. So we've created a complete, albeit simple, RAG implementation using only LangChain components and integrations, starting at external document loading, splitting, embedding, and uploading, and then concluding, and then conducting on-the-spot retrieval based on a user's query to a GPT-4o inference model, and then we printed out the results. So if you use this notebook as a base in your own time, you can experiment by adding any components that you want, swapping them out, creating some cool applications with the LangChain framework. So hopefully you have a bit of a better understanding of how to use it, and thank you for listening.